We can also use R to carry out some matrix algebra calculations. One of those important calculations is the computation of eigenvalues and eigenvectors. So let's define, to start working with an example, let's define a matrix. This is a square matrix with numbers 1 through 9, 3 rows and 3 columns. That is our matrix. And now we're going to compute eigenvalues and eigenvectors using the built-in function eigen. All I did here was to type the name of the function or some of the characters on this built-in function, and then I use the tab command, the tab key stroke, and R automatically gives me a list of the name of that built-in function with a list of the input arguments. Okay, so we need to specify the matrix, and also I'm going to call this output, I'm going to give this output a name. I'm going to call this my evals. Okay, all I'm saying is that the output of this built-in function, eigen, is going to be stored on this variable, a variable that I chose the name for. And if I'm not sure of what that variable is storing, since it's the output of some built-in function, I can use the command names. Names is basically an interrogation of what are you holding. Names gives me back that variable my evals has an attribute called values and another attribute called vectors. I can access that information by using the dollar signs. For example, I can say my evals $ values, and this gives me a list of the eigenvalues which are stored under that attribute. So notice again the use of the dollar sign. And if I type my evals $ vectors, then this gives me a list of the eigenvectors of that matrix. Okay. Now, a useful thing is to identify which of these eigenvalues has the largest, which is the so-called dominant eigenvalue. Okay, so for this we will need to make use of the calculation of the real part of an eigenvalue. So that's not and in this case this matrix is such that all the eigenvalues are purely real. Okay, so let's work with a matrix that has complex eigenvalues. So let's say we redefine A, or let me work now with a matrix B. Okay, so this matrix has, say this is going to be, we're going to put together some columns. Okay, 3 columns. The first column has numbers 3, 2, 0. The second column has numbers 0, 2, 3. And the last column has numbers 0, -3, 1. Okay, so here's the first column 3, 2, 0, second column 0, 2, 3, last column 0, -3, 1. Let's take now a look at, say this is B, that's my output, B, let's say B dot EIG, this would be eigen of B. And remember that output B.EIG has an attribute called values. This will list the eigenvalues. So there is the first eigenvalue here is the second eigenvalue, here is the last eigenvalue. So what we notice is that now these eigenvalues have the letter I. Let me see, I want to see at the first one. There's the first one, the first eigenvalue. And let me see at the last eigenvalue. This I equals the square root of -1. This is the definition of a complex number, okay? So when the eigenvalues are complex, answering the question of which of these eigenvalues has the largest real part is an important question, okay? So there is a function called RE for real part. This function will compute the real parts of the eigenvalues. So here, this is basically extracting. Look at here's the first eigenvalue. The real part of that is 1.5. The imaginary part of that is the number that is multiplying the letter I, right? So by doing RE for real, we're extracting the real parts of these eigenvalues. So now what we'd like to do is to determine which of these is the real part with which eigenvalue has the largest real part. So let's say that we type something like R max, and this is going to be the name of that output. This is the maximum of real part of B and here we're looking at values, and so this R max is 3. And if we would like to store which of those is the one that has the largest real part, we will do something like this. We would use the command which has a real part that is equal to R max, real part of B, that EIG values. Okay, so this would be storing the index for the eigenvalue that has the maximum real part. Therefore, we can say something like, okay, so now be that EIG values, and square bracket here we put the letter J. This will be the eigenvalue corresponding to that one that has the largest real part. Okay, and if also we would like to keep track of the eigenvector that corresponds to the eigenvalue with the largest real part, then we can type here we can type this, right? J is the index of that eigenvalue, and this is the eigenvalue with the largest real part, and its corresponding eigenvector is given, this will be in this case we have to specify inside the square bracket, we have to leave one space blank, comma, and that followed by the index. In other words, we're extracting column number 3, and this will give us this vector, which is the eigenvector of the eigenvalue with the largest real part. And this concludes our discussion on the computation of eigenvalues and eigenvectors using R.